And so I've got a little density 3D printed cube right here.
Yeah,
For those who are listening, made of aluminum. So when like specifically to additive, right? You've got this challenge. You kind of hinted on it with anisotropy because you're building layer on layer, and the part is oriented in different directions, even if you're testing in one. So like when you were to if you were to do something like this, like kind of indented or get a tensile coupon or something like that, do you have to be pretty careful of what, like understanding which direction that it was built in? And so like if it was built kind of like this, may want to do it like this, but if you rotated it 90 degrees, you'd get kind of a completely different result or potentially a different result. Is that
yeah, for
a
sure.
big big characteristic you need to track?
Yeah, so there's two, I guess, really important things that are about additive, and the first one is anisotropy, and the second one is if the structure is homogeneous or not. So if we touch on the anisotropy one first, so if you have a material that you've built up, if you do an indent along the build direction, so if you imagine you've built up the part, you're kind of indenting on the top of it, then we would expect in the vast majority of cases for that to give us a radially symmetric indent. So, i.e. that the properties are the same in all of those in plane directions, if you like. And that's because where you often see the differences is not in the XY plane. So you'd expect the properties, if you did like an X bar or an XY bar, to be pretty similar. The differences we really see are when you're looking at the plane that contains the build direction. So if you took that part like you've got there and then rotated 90 degrees and did an indent in either the XZ or the YZ plane, where you often get things like directional growth or strong crystallographic texture, that's where you can start to see these non-radially symmetric indents, which give us a red flag to say, okay, there's a difference in the properties here between, for example, the build and the transverse directions. And you know, if we spin that the other way, we've got a really quick way of assessing if anisotropy is present in a material. So you could take your density cube there and you could do an indent on the top surface containing those XY planes. You could get a prediction of the properties. And okay, that's going to be, if you like, averaged over all directions. You could then flip that material and you could get a really quick sense of, is this material strongly anisotropic or not? And at the moment, you know, we can give you an indication of how strong the anisotropy is, but we can't sort of quantitatively do it. And that's where we're working towards in the future. But even now, that's quite powerful to be able to say, inform what tensile testing you might do or what heat treatment you might apply, etc. So the other thing about additive, and this is again one of those things that is a bit of an issue in terms of the materials, but also a benefit of using a technique where you're probing sort of single points. You know, with your typical tensile test, you're talking tens of millimeters of material that you need to pull on, and you'll end up with one tensile test result, right? You just get one yield stress and one ultimate tensile strength, and that's it. You're not given any information about, do the properties vary over that bar? Which, you know, if your process is like additive, where there can be some differences in the different locations of the build plate, for example, you couldn't always be sure that the whole structure is homogeneous. And using our technique, you can then do more of a map over the whole build plate and see, okay, are my properties in these different locations that I'm printing always the same? What we found a lot of the time is that they're not. You know, these different regions will have been through different thermomechanical cycles, and that will lead to differences in the material properties.